So first, I would like to thank the faculty for giving me an opportunity to come share a little bit of what I think about. And I guess with that, let me get started. So I'd like to tell you about the thin obstacle problem today, and give you some history about what's proven and some actually interesting open questions. So the first question you're probably asking is, what is the thin obstacle problem? And it's a minimization problem. If I can, wrong way. And what we're asked to do is minimize the Dirichlet integral. Here x is a point in Rn plus 1, and I'm going to denote the first n coordinates by little x and the last coordinate by y, and you'll see why, over this set here, which is a set of functions v that are even with respect to this extra coordinate, have some prescribed boundary data g, and are prescribed to live above some constraining function phi that lives only on this sort of codimension 1 hypersurface, okay? So it's a thin obstacle, okay? And so if you want a picture to keep in mind, I guess think about a hiking tent, right? So let's say instead of B1, you've got a square.
What is B1?
So B1 is the unit ball in Rn plus 1, okay? So let's see, if I can draw a picture. Great. And then, I don't know, here's your door to your tent. Okay, so here's a tent somewhere in the woods. And in this particular case, our boundary data is this piece here. Okay, and our thin obstacle is going to be this sort of central piece, this hump that allows you to keep the tent standing. Okay? And so we consider this problem, and you might sort of, yeah.
What are G?
So G is some prescribed boundary data, right? So in this case, it's the orange, okay, if I look at the picture. And phi is just some given constraining function, which I call the obstacle, and my solution has to live above that obstacle, right? And so the easiest thing to do is look at the picture, right? So the orange guy is G, and the yellow guy is phi, or the graph of G and the graph of phi. Right? And the tent itself is going to be my solution. Does that make sense? Okay. All right, so you might say, great, so I've got this problem and, real world motivation. You're sending out there camping and you say, well, I've got this tent. Well, is this tent somehow structurally sound? Does it make sense? If I was a mathematician, how would I go about constructing it? And this is, I guess, your first order approximation to this tent. Okay. So, as I said before, this function phi is called a thin obstacle, and why we call it thin is because it's, well, a codimension 1 object with respect to the ambient space, which is Rn plus 1. And the set y equals 0, or Rn cross 0, is called the thin space. Okay? And so the first question you might ask is, well, do solutions exist? I mean, we know tents exist, but in the mathematical framework, do they? And it turns out, yes, and uniquely so. And then the second question you might ask is, well, what does my tent look like, right? What might be the regularity of my unique minimizer? And what's the geometry of this free boundary, which is an a priori unknown of the equation, or problem, which is the topological boundary in Rn of the coincidence set between you and my obstacle. Okay, so in this picture, my coincidence set is going to be this green piece here. Right? My non-contact set is going to be where I lift away, and my free boundary is just these 2 points here. Okay, so in 1 dimension, or I should say 2 dimensions, where my thin space is 1-dimensional, things are, well, pretty easy to see, but kind of difficult to study. And so you say, okay, well, I've got these questions, right? And let's try to figure out how I might go about answering them. So to study model behavior, we're going to sort of take this picture and turn it upside down, and we can essentially subtract off the obstacle and pretend the obstacle is 0, okay, just mathematically. Or you can just think, well, for simplicity, since I want to study model behavior, let's think of the simplest obstacle I can pose, which is nothing. Okay, so this picture doesn't really make sense anymore, but mathematically this makes perfect sense. So in R2, besides the tent, we've got some concrete mathematical examples. which just come from complex analysis, which are just the real part of x plus I absolute value y to the power k, or kappa, where kappa is one of these integers, right? Or actually numbers. Well, so I've got the even integers, the even numbers, sorry, and then 2m minus 1/2, okay? And maybe let me draw you some pictures of the case when kappa equals 2, for instance. So here my thin space again is just a line. I've got this quadratic polynomial, right? And then I'm sort of looking at something that looks like this. Okay, and so here my contact set and my free boundary are just 1 point. And then in the other case, say when kappa equals 3/2, this corresponds to when m equals 1, I'm going to get a picture where I have something that looks like this. So this is now bad because I don't have space. Okay, but the point here is that I have a contact set which is sort of half line. My free boundary is again a point, but then I lift up and I have a non-coincident set, right, which is going to grow like, well, the power 3/2, right, distance from this origin point. Okay? And so great, we've got this nice family of examples and their solutions subject to their own boundary data. And we might say, okay, well, sort of what does this tell you? Well, if you look at sort of the regularity of these solutions, you see that the worst thing possible is this example here, right? And you see in particular that this guy or this function is going to be C1 1/2 on either side of this thin space, and in fact up to the thin space, but only Lipschitz across. Okay, so at least from this family of examples, we might say, okay, well, the optimal regularity of the solution is exactly given by this prototypical example. And that was proven by Athanasopoulos and Caffarelli. I don't remember exactly when, but they proved exactly that. That my solution has an optimal regularity, which is C1, and the gradient as a Holder modulus of continuity with that exponent 1/2, locally on either side of this thin space, including it, but only Lipschitz across, right? Because here I have some corner. So great. So that sort of regularity question, or part 1, we've got answered. And you might say, well, what happens next? Right? And you look at these examples again, you say, okay, well, there's sort of a natural dichotomy that's showing up, right, with respect to free boundary points and the contact set. And those are going to be, well, first, the Hn positive density points, which correspond to, say, this example, right, where I have a contact set that's basically n-dimensional, and then my free boundary is sort of looking like what you'd expect the boundary of a smooth set to be. Okay? And then I've got this other example, which is the Hn zero density points, or n0 n-dimensional points, which correspond to this picture here. Right? And somehow this dichotomy is telling you, well, maybe these are the only two, well, these are the only two possibilities, right? But somehow can I understand this further? And so you'd like to say in some senses that this first set, this positive density set, is like a regular set, right? If I think of a smooth set and I look at a boundary point, well, what's the density of that point? It's 1/2, right? If I zoom in, right, that smooth boundary is going to flatten out and I'm going to get a half space. Okay, so this corresponds to half density. And we're going to think of maybe these zero density points as singular points because they're kind of super skinny. All right? And you say, well, I mean, how do we go about studying this dichotomy? Right? And it turns out, well, if we think about what the free boundary is, it's just a zero-level set of a function. Right? And so from that point of view, a finer understanding of the regularity at free boundary points, maybe an explicit Taylor expansion, will do the job. It's going to give us some understanding of the structure and regularity of the free boundary. Make implicit function theorem. Okay? So then what happens is, well, we enter Almagren, right? So Almagren has this wonderful frequency function, which is this quotient of r times the integral over br at some point of the gradient u squared divided by essentially its average, the L2 average on the boundary. And it turns out that this function here is increasing at every free boundary point. Okay, so you might say, well, what is this object? Why is it important? Well, if we just recall what happens with harmonic functions. So look at this object for harmonic functions, right? And you can prove that it's increasing. So you can take the limit as r goes to 0, and you're going to get some unique number, right? And that unique number, say at the point where, say my harmonic function is 0 at that point, otherwise I have to do a little change at the bottom there, is just going to be the value of the homogeneity of the first non-zero piece in the Taylor expansion of my harmonic function, right? So if it starts off with like something like x squared minus y squared, right, then the value at 0 would be 2. Okay, really easy exercise. I encourage you all to do it. So what this does is it's basically saying that if each free boundary point, we can identify a unique number, which is going to tell us about the infinitesimal behavior of u at that free boundary point. Essentially, what's the order of the first part of the Taylor expansion of u at that point. Right? So what happens next is you say, okay, well, what are these possible values? And it turns out that there's a minimal value, and then there's a potential whole continuum of other values. And it turns out that this minimal value, this 3/2, which corresponds to this picture, right, can be put together in a relatively open subset of the free boundary. And it turns out that that subset is going to be a C1 alpha submanifold. Okay, at least initially. This was proven by Athanasopoulos, Kefrel, and Seltzer. And then it turns out that, well, you notice that this is a subset of the positive density points, because these are all half density. But we don't know if it's everything. Okay? And then you might ask, what about higher regularity? Right? I said a C1 alpha submanifold. But maybe you expect that this submanifold should be more regular based on the regularity of my obstacle. And it turns out that that's true, and this was proved by first De Silva and Savin in the case when the obstacle is 0. They were able to prove that the free boundary is smooth at these sorts of points. And then I and a collaborator extended that to non-zero obstacles, along with another team, Cook, Ruland, and Shi. So you're saying, okay, great, so we've got some semblance of what's going on here, but what's next? So it turns out just after that paper, another paper was put out, which studies the even frequency points, right? Which I know exist based on this example, or that family of examples. And it turns out that these are precisely the HN zero density points, right? There's nothing else. If I have a zero density point, it has to have an even frequency, right? And if I have an even frequency, it has to be a zero density point. And so in the literature, these are called singular points, and in this paper by Gruffalo and Petrosian, they're able to prove that this set is contained in the countable union of C1 submanifolds. Okay? And so then you might ask, well, again, what about higher regularity, right? Can I maybe improve the regularity of this containing set of manifolds to something better? And recently it was proved by Colombo, Spolauer, and Velchakov that you can improve this quantitatively to a log epsilon modulus of continuity. And then if you throw away a lower dimensional set, you can actually improve the regularity of the containing manifold to C2. Okay, and with respect to that C2 or that lower dimensional set, we expect somehow that this to be sharp. There should be examples where, there'll be some subset of points where you actually can't put it in a C2 manifold. But this hasn't been proven. Okay, so what does that mean? It says, well, what are the open questions that are left? Well, the first one is, of course, determine all of these achievable frequencies, i.e. the value Almogren function 0. Okay? At the moment, we have some information about that, but really, we're pretty far from understanding what are all the values. And a second question might be sort of complete the high regularity picture for these singular or HN0 density points. Right? Just like we were able to say that the regular portion, this minimal frequency set, was contained in, say, a smooth submanifold when the obstacle was smooth, can we say something along the lines that's similar, right? That outside maybe a lower dimensional set, the containing manifolds for the singular portion that we're calling would actually be smooth submanifolds. All right? And with that, I'd like to thank you.